In the early hours of August 26, 2017, a burst of radio energy arrived at Earth from a source 3 billion light-years away. That alone was not unusual. We detect signals from deep space regularly. What made this one different was its structure. Every radio signal we had ever picked up from space was either a single explosion of energy followed by silence, or a perfectly repeating pulse, like a metronome. This one was neither. It had pulses of different intensities, different durations, and different spacings. Some of its patterns appeared more than once on the spectrogram. They looked like distinct, repeating symbols. Not a random burst, not a clock, something in between. For the first time, scientists were looking at a signal from space that had the structural properties needed to carry information. And that raised two of the most important questions in modern science. How do we tell the difference between a signal produced by intelligence and one produced by nature? And if we ever did receive something genuinely intelligent, how would we begin to understand it? Those questions do not have simple answers. But over the past century, scientists have quietly assembled a remarkable set of tools to approach them. Tools built from physics, mathematics, linguistics, and most recently, artificial intelligence. What follows is the story of how those tools were developed, what they reveal about the nature of intelligence itself, and why the signal from 2017 sits right at the edge of what we can currently explain. The entire field of radio astronomy began by accident. In February 1942, British military radar stations along the southern coast suddenly filled with interference. The assumption was enemy jamming, a standard wartime tactic of flooding radio frequencies with noise to blind the opposition. But physicist James Hay noticed something that did not fit that explanation. The noise moved. It drifted slowly across the sky in exact step with the sun. It was not coming from Germany. It was coming from 93 million miles above their heads. Hay contacted the Royal Observatory, and they confirmed that a massive sunspot had been active, an eruption on the surface of the sun that was flooding space with radio energy. That single observation opened a new window on the universe. Instead of looking at the sky with visible light, which our eyes naturally detect, we could now listen to it in radio waves, a form of light that is invisible but carries just as much information. A radio wave is simply light vibrating at a frequency too low for human eyes to register. On Earth, we create it with an antenna, which is a loop of wire through which we push electrical current back and forth at a specific frequency. When that oscillating current runs through the wire, it radiates energy outward as a radio wave. To detect it, you need another wire somewhere else. When the wave reaches that wire, it pushes a tiny oscillating current through it at the same frequency. That faint current is what we amplify and measure. The sun is powerful enough that even a relatively small antenna could pick it up from Earth. But to detect quieter sources much farther away, you need far more sensitive equipment, which means a much larger collecting area. More wire means more signal and a better chance of detecting something faint against the background noise of space itself. That is exactly what a 24-year-old graduate student named Jocelyn Bell did in 1967. Working at Cambridge University, she and her colleagues strung miles of wire across 4.5 acres of open field, supported by a forest of wooden posts. This enormous wire grid was connected to an amplifier and a chart recorder that plotted the total detected radio energy as a wavy line on paper. She was scanning the sky, looking for distant bright radio sources called quasars. If you build a radio receiver and do this yourself, the first thing you notice is that even pointing at an apparently empty patch of sky, there is always a faint background hiss. This hiss had been identified in 1933 by physicist Carl Jansky, who discovered that the noise became louder when the antenna was aimed at the bright band of stars we see crossing the night sky, which we now know is our own galaxy seen from the inside. The entire Milky Way is gently humming in radio, and this background glow is now measured in a unit called the Jansky in his honor. It is the baseline everything else must rise above. To make sense of a detected signal beyond just its total energy, scientists use a technique called spectral analysis. Just as a glass prism splits white sunlight into a rainbow by separating it into component wavelengths, radio signals can be mathematically split into their component frequencies. The result is a spectrogram, a visual map with frequency on one axis, time on the other, and brightness representing the amount of energy at each combination. A spectrogram is essentially a fingerprint. It shows not just that energy arrived, but exactly what kind of energy arrived and when. If you do this with a human voice, The spectrogram shows energy spread across many frequencies at once. This is called broadband. A solar flare looks similar, an explosion of energy scattered across many frequencies simultaneously. But the simplest thing an antenna can transmit is a signal at a single precise frequency, a single bright line on the spectrogram. This is called narrowband. A radio telegraph works this way. One frequency switched on and off in short and long pulses to represent dots and dashes. When scientists first began scanning the galaxy for narrowband signals, the first one they found was in 1951. It appeared at a frequency of 1,420 megahertz. This was not a mystery. Hydrogen, the most abundant element in the universe, naturally emits radio energy at exactly that frequency, like a tuning fork vibrating at a specific pitch. Wherever hydrogen clouds float in space, they quietly broadcast at 1,420 megahertz. The universe is full of this tone. In 1959, physicists Philip Morrison and Giuseppe Cocconi published a landmark paper that launched the scientific search for extraterrestrial intelligence. Their argument was straightforward. Any civilization that developed radio astronomy would discover hydrogen's frequency early. It is one of the first things radio astronomers encounter. And the region of the spectrum around hydrogen's frequency is one of the quietest parts of the entire radio dial, relatively free from interference. So if you were an intelligent civilization trying to send a signal that another civilization might notice and recognize, putting it near the hydrogen frequency would be a logical choice. It is a cosmic landmark, a frequency every radio-capable civilization would know. That reasoning made the events of August 15th, 1977, so electrifying. A radio telescope at Ohio State University, known informally as Big Ear, detected a narrowband signal arriving at exactly 1,420 megahertz. It lasted 72 seconds and was 30 times stronger than the background noise. An astronomer named Jerry Eman was reviewing the computer printout of the night's data when he spotted it. He circled it and wrote a single word in the margin: wow. The signal has been known as the wow signal ever since. Scientists immediately hoped there might be structure hidden within that signal, perhaps subtle variations encoding information. But when they examined it closely, the variations inside the pulse appeared to be nothing more than random fluctuation, consistent with noise accumulated during a journey across deep space. The signal gave no return address, left no further message, and has never been detected again. To this day, after decades of searching, its origin remains genuinely unknown. Jocelyn Bell's discovery in 1967 had a different outcome. In November of that year, she noticed something unusual in her chart recordings. A short, sharp spike of energy, repeating at a precise interval of 1.3 seconds. It came back every 1.3 seconds like clockwork. It was so regular, so mechanical in its precision, that she and her colleagues half-jokingly labeled the source LGM1, standing for Little Green Men. It felt too artificial to be natural, but when they examined each pulse in detail, they found no hidden message inside. Each pulse looked slightly different from the others, but the variation was irregular, inconsistent with any intentional encoding. The pattern from pulse to pulse was statistically indistinguishable from noise riding on top of the signal. What Bell had discovered was not a transmitter built by an alien civilization. It was a pulsar, a neutron star, which is what remains after a massive star collapses. A neutron star packs more mass than our sun into a sphere roughly 20 kilometers across. As it spins, it sweeps a beam of radio energy through space, like a lighthouse beam sweeping across the sea. Earth happened to lie in the path of that beam, and every 1.3 seconds, the beam swept past us. The precise timing was not intelligence. It was physics. This raised an important problem. If we were searching for signals from alien civilizations, and a naturally rotating collapsed star could produce something that felt artificial enough to briefly consider alien origin, we needed a much sharper filter. The precision of a pulsar's timing did not come from a mind. It came from the conservation of angular momentum, the same physics that makes a spinning ice skater speed up when they pull in their arms. How do we distinguish what minds produce from what nature produces without a mind? To build that filter, we first need to understand what nature actually does produce on its own. Consider the simplest form of randomness. At the smallest scales, energy is bouncing around everywhere. If you take the surface of water and measure whether a tiny patch is being pushed up or down at any given instant, the answer is essentially 50-50, equally likely in either direction. Pure randomness at its most basic level is a coin flip repeated endlessly. But what happens when you add many random events together? The behavior changes in a predictable way. The classic demonstration is a pegboard, sometimes called a Galton board. Imagine a vertical board with rows of pegs arranged in a triangle. A ball dropped from the top hits the first peg and bounces either left or right with equal probability. Then it hits another peg and bounces again. After passing through many rows of pegs, the ball reaches the bottom. The end result is that balls cluster toward the middle, because there are many different paths that lead to the center and very few paths that lead to the extreme edges. Only a ball that goes the same direction at every single peg reaches the far edge, and that is vanishingly rare. The resulting pile of balls follows a specific mathematical shape called a Gaussian distribution, also known as a bell curve. It peaks in the middle and tapers symmetrically on both sides. Carl Friedrich Gauss described this shape in the early 19th century, and we see it everywhere. Human heights, variations in air temperature, the brightness of stars measured repeatedly. Whenever a measured quantity is the result of many independent random events, a Gaussian distribution appears. The background hiss between radio stations follows this shape. It is the statistical signature of randomness without memory. But not all randomness is memoryless. In 1951, a British hydrologist named Harold Hurst published the results of decades of work analyzing the flood records of the Nile River. He had gone back through centuries of historical data and found something that pure randomness could not explain. High flood years tended to cluster together in extended runs. Low flood years did the same. The river appeared to have a kind of memory, not a cycle, not a pattern that repeated on schedule, but a momentum. Whatever was happening now made similar conditions slightly more likely in the near future. This kind of randomness with momentum is called colored noise, in contrast to white noise, which has no memory at all. You can visualize colored noise with a modified pegboard. Imagine the board itself is pivoting on an axle. A run of balls landing to the right causes the board to tilt that way, increasing the probability that the next ball also goes right. A run to the left tilts it back. The center drifts, wandering over time in ways that white noise never would. The important thing for the purpose of building an intelligence filter is this. If you take any naturally occurring signal, whether it is white noise, colored noise, or any other random process we know of, and rank the most common measurements from most frequent to least frequent, you get the same basic shape. A smooth, rounded curve that bulges toward the common end and tapers off toward the rare end. It is convex, like the top of a hill. This is a statistical fingerprint of nature. In the 1940s, a linguist named George Zipf set out to understand the statistics of human language, and what he found was something completely different. He took a book, counted how often every word appeared, and then ranked those words from most common to least common. The most common word in English is the word the. The second most common is something like of, and then the frequency drops, but it drops in a very specific way. If you plot this on a graph, with word rank on one axis and frequency on the other, you do not get the rounded, convex shape of natural randomness. Instead, you get a concave shape, sharply steep at the start and gradually leveling off. When Zipf compressed both axes to see the full range at once, this concave curve straightened into a perfectly clean straight line. In mathematics, that kind of relationship is called a power law. The slope of that line, when plotted appropriately, was consistent across every book Zipf analyzed and every language he examined: English, French, German, Chinese. The slope was always the same. This pattern is now called Zipf's Law, and it appears to be a universal signature of language. It was immediately exciting to scientists thinking about how to search for extraterrestrial intelligence. If a signal obeyed Zipf's law, perhaps it was coming from a mind. But then a complication appeared. In 1944, geophysicists Benno Gutenberg and Charles Richter were studying earthquake data, and they discovered the same shape in the size distribution of earthquakes. Many small quakes, fewer medium ones, and very few enormous ones, following the same power law slope that Zipf had found in language. And the reason they found this shape had nothing to do with intelligence. You can demonstrate the reason with nothing more than a pile of rice. Drop grains onto a pile one at a time. Most grains land and nothing happens. Occasionally, a grain lands and causes a small avalanche. Very rarely, one grain triggers a cascade that reshapes a significant portion of the pile. If you measure these avalanches and rank them by size, you get a power law curve, the same shape as Zipf's law. the same shape as the frequency distribution of words in language. This is because the pile of rice is what physicists call a self-organized critical system. It builds up stress gradually and releases it in bursts. The distribution of burst sizes follows a power law regardless of the specific mechanism. Earthquakes work the same way. Lightning strikes, avalanches. None of these require a brain. And this is the leading scientific explanation for the 2017 fast radio burst that started this story. The most probable source is a magnetar. A magnetar is a neutron star, a collapsed stellar remnant like a pulsar, but with a magnetic field roughly 1 quadrillion times stronger than the sun's. That magnetic field exerts enormous forces on the star's crust. Over time, stress builds up. Occasionally, the crust cracks, releasing a starquake. Energy is discharged in a burst. And the statistics of those bursts, the distribution of their sizes and spacings, can follow a power law, producing a spectrogram that looks eerily like the fingerprint of language, without containing any message at all. So Zipf's law is not a sufficient filter. Nature can produce it without help from any mind. Something deeper was needed. The next step came from Shannon, a mathematician who worked at Bell Labs in the 1940s and laid the foundations of modern information theory. Shannon was not just interested in how often individual symbols appeared. He wanted to understand the deeper structure of how symbols followed each other. In any language, the probability that a given symbol appears is not independent of what came before it. In English, the letter Q is almost always followed by U. The word the is rarely followed by another the. The phrase I went to the is far more likely to be completed with a place name than with a verb. The structure of language is not just in the individual frequencies of symbols. It is in the relationships between sequences of symbols. Shannon measured this by analyzing not just how often individual symbols appeared, but how often pairs appeared, then triples, then longer sequences, and he found something that pointed to a fundamental difference between language and noise. In language, as you analyze longer and longer sequences, the statistics become increasingly constrained. Knowing 10 previous words gives you a much better prediction of the next word than knowing just one previous word. The entropy, which is the technical term Shannon used for the amount of surprise or unpredictability, decreases as you look at deeper and deeper sequences. The signal becomes more predictable the further back you look. This predictability keeps growing without limit in language. The deeper you examine, the more structure you find. Noise behaves completely differently. In any naturally occurring signal we know of, knowing the previous few values tells you almost nothing additional about the next value compared to knowing just one previous value. Looking deeper into a noise signal does not help you predict it. The entropy stays flat regardless of how far back you look. This difference, how entropy changes as a function of sequence depth, is the intelligence filter proposed by Lawrence Doyle at the SETI Institute. Plot entropy on the vertical axis and sequence depth on the horizontal axis. Natural signals of all kinds, white noise, colored noise, pulsar timing, earthquake sequences, all stay roughly flat. They do not reward deeper analysis with better predictability, but language of any kind drops. The deeper you look, the more predictable the next symbol becomes. The entropy curve goes down. What makes this filter powerful is its apparent universality. When researchers applied it to dolphin communication, which evolved completely independently of human language over millions of years with no shared ancestor, they found the same dropping entropy curve. Dolphins show the same mathematical signature of structured communication that human languages do. Two completely different species, no shared evolutionary history, the same information theoretic fingerprint. When researchers applied the test to the 2017 fast radio burst from 3 billion light-years away, the result was tantalizing. The signal passed parts of the filter. Its symbol frequency distribution showed a shape reminiscent of language rather than random processes. But the deeper analysis was ambiguous. The signal does not conclusively pass all aspects of the test. The magnetar interpretation, drawing on the same mathematics that describes earthquakes and avalanches, remains the leading scientific explanation. But scientists cannot yet definitively rule out a more exotic origin. Now consider what would happen if a signal passed every test. If entropy dropped with depth in a way that definitively exceeded anything nature could produce, the next challenge is staggeringly harder: understanding what the signal is actually saying. Shannon himself worked on this problem. He realized that if you understood the statistical structure of a language, you could run it forward in a simple way. Just look at the frequencies and sequences you have measured, and select the next symbol according to the probabilities you have learned. He tried this with English text, building a simple statistical model and using it to generate new text. At the simplest level, just picking letters according to their individual frequencies, the output looked like random jumble. At the next level, choosing pairs of letters according to their observed frequencies, vaguely English-shaped patterns began to emerge. At the third level, using triples, the text started to look remarkably like English words, even though it was generated statistically rather than written by a person. Shannon recognized that to capture the long-range structure of language, the kind of coherence that makes a paragraph about one topic rather than random thoughts, his statistical machine would need to look hundreds of symbols deep. He estimated the amount of memory required would be computationally impossible to build. He filed this away as a theoretical limit, something interesting, but practically unreachable. He was right for several decades. It was not until the early 21st century that computers became powerful enough to approach what Shannon was describing. And the form that capability took was not quite what anyone had anticipated. Large language models are neural networks trained on a single task. Given the previous sequence of text, predict the next word. The training process involves adjusting billions of internal parameters until the model becomes extremely good at this prediction task across enormous quantities of text. What emerged from this process was not a simple lookup table of statistical frequencies, as Shannon had originally imagined. It was something geometrically richer. When researchers examined the internal representations of these models, they found that concepts were being stored as locations in a high-dimensional geometric space. Words with related meanings were positioned near each other. Words with opposite meanings were positioned in opposite directions. The word for cold in Japanese sat in the same relative geometric position to the word for hot in Japanese as the English equivalent did in English. The geometric relationships between concepts appeared to be consistent across languages. This is why large language models can translate not by looking up words in a dictionary, but by rotating the geometric shape of meaning from one language's coordinate system into another's. The shape of the concept is preserved, only its expression in symbols changes. Researchers at the Massachusetts Institute of Technology recently applied a similar approach to the click sequences produced by sperm whales. These animals produce elaborate patterns of clicks called codas, and researchers have long suspected these clicks carry social information. The neural network was trained on thousands of hours of whale vocalizations, alongside observations of whale behavior. The resulting model could predict what a whale was about to do, whether it was about to dive, surface, or engage in social interaction, with nearly 90% accuracy. The model had learned the structure of the clicks well enough to make meaningful predictions about behavior, even though researchers still cannot tell you what any specific click sequence means in the way you might translate a sentence. This is a new kind of understanding. Not translation in the conventional sense, but recognition of structure. The model does not know the whale's language. It knows the shape of the whale's language, and that shape contains enough information to be practically useful. The same approach is now being considered for anomalous signals from space. If a signal ever clearly passes the intelligence filter, if its entropy profile drops in the way that only structured communication produces, a large language model trained on that signal could potentially begin to extract something about its internal structure. It would not immediately translate it, but it might identify which sequences are grammatically similar to each other, which might correspond to nouns versus verbs, which clusters of sequences tend to appear in similar contexts. It would find the shape of the meaning before anyone could say what the meaning was. This is, of course, deeply uncertain territory. Every step involves assumptions that may not hold for a truly alien communication. A civilization that evolved under completely different physical and biological conditions might encode information in ways that do not follow the same mathematical patterns that all Earth life happens to share. Their communication might have an entropy profile that drops differently, or rises, or oscillates, in ways none of our current models are designed to recognize. There is also the question of whether the sender intends for us to understand. A deliberate interstellar message designed to be decoded would presumably be constructed to be interpretable by any radio-capable civilization, which means it would likely rely on universal mathematics and physics rather than cultural specifics. The prime numbers, geometric relationships, physical constants, these are the same everywhere in the universe. A civilization trying to communicate would presumably start there, but a signal not intended for us, a leak of internal communications, or a navigational beacon, would have no such consideration built in. The WOW signal of 1977 has never returned. Dozens of follow-up observations have been made of the same patch of sky over the intervening decades, using instruments far more sensitive than the Big Ear telescope that first detected it. Nothing has ever appeared again in that location, at that frequency. One leading hypothesis is that it came from a comet or a cloud of hydrogen gas, illuminated by an unusual solar event, which would explain its appearance at the hydrogen frequency and its non-recurrence. Other researchers argue this explanation does not fully account for all of the signal's characteristics. The debate continues. The 2017 fast radio burst, known scientifically as FRB 171220, was detected by the Canadian Hydrogen Intensity Mapping Experiment, a radio telescope array in British Columbia. It was the first fast radio burst ever observed to repeat, which immediately made it scientifically unusual. Most fast radio bursts appear once and are never detected again from the same location. The repeating nature of this one allowed astronomers to point other telescopes at its source, and eventually determine that it was coming from a galaxy 3 billion light-years away, making it the most distant source of a repeating fast radio burst at the time of its discovery. The repeating bursts showed the complex internal structure that generated so much interest. Different intensities, different durations, different subpulse spacings. The mathematical analysis that suggested structural similarities to language was published by researchers who were careful to note that this does not mean the signal is intelligent in origin. It means the signal has a statistical profile that does not immediately exclude intelligent origin using the tools currently available. The magnetar explanation remains far more consistent with the totality of what we know about the physical universe. What makes the field so intellectually compelling is precisely that gap. We have developed mathematical tools sophisticated enough to ask the question of whether a signal carries intelligence. But nature is also sophisticated enough to produce signals that partially mimic the signatures we associate with intelligence, without any mind being involved. The tools have to become sharper before we can be confident in what we are measuring. Lawrence Doyle's entropy-based filter represents the current state of the art in the scientific search for extraterrestrial intelligence. But researchers are working to refine it. One direction is to characterize more natural signals and verify that they all stay flat on the entropy depth curve. Every new type of astrophysical source that gets analyzed and confirmed to be flat strengthens confidence that anything which does drop is genuinely unusual. Another direction is to examine more biological communication systems with the same tools, not just to look for alien signals, but to understand what the entropy signature of intelligence looks like across the full range of Earth life. Bees, cephalopods, corvids, cetaceans. Each species that shows a dropping entropy curve adds a data point, confirming that the test is measuring something real about the nature of structured communication. There is also an ongoing technical revolution in the sensitivity of radio telescope arrays. The Square Kilometre Array, currently being constructed in South Africa and Western Australia, will be the largest radio telescope in human history when it is completed. Its collecting area, distributed across thousands of individual antenna elements coordinated by supercomputers, will exceed 1 square kilometer in total. This represents an improvement of several orders of magnitude over previous instruments. Signals that would have been invisible to every telescope we have ever built could become detectable. The speed at which signals can be analyzed is also increasing rapidly. Digital signal processors can now examine billions of channels simultaneously in real time, something that required months of dedicated computation just a few decades ago. This means that a signal appearing briefly and unexpectedly, as fast radio bursts tend to do, can be captured in its full detail before it disappears. At the same time, artificial intelligence systems trained on vast archives of known astrophysical signals are being deployed to scan incoming data for anomalies, flagging anything that does not match known natural sources for human review. This approach already led to the discovery of dozens of new fast radio bursts in archival data that had gone unnoticed in initial processing. Training these systems to recognize the specific mathematical signatures of structured communication rather than just physical anomalies is one of the next research frontiers. The deeper question running beneath all of this is one of perspective. Our entire understanding of what intelligence looks like is based on a sample of one, life on Earth. Every structure in our filter, from Zipf's Law to Shannon entropy to the geometric representations in large language models, was built by studying Earth languages and Earth biology. These tools have shown enough universality across Earth species to suggest they might extend beyond our planet, but that is still a vast, inferential leap. A signal that comes from 3 billion light-years away, from a source that evolved under conditions we cannot directly observe, carrying information in a medium shaped by physics we may not fully understand, might look like nothing we expect. It might be so structured that our current tools register it as random, because the structure operates on timescales or frequency ranges outside what we are measuring. Or it might be so alien in form that it does not map onto any of our existing categories at all. This is not a reason to stop looking. It is a reason to look more carefully and with more tools. The history of radio astronomy is filled with moments where something looked like noise until better instruments revealed structure, or something looked structured until better analysis revealed it to be noise. The field advances by building sharper filters and then honestly applying them to what the universe sends us. The signal from 2017 did not turn out to be a message. The best current evidence points toward a neutron star with an extraordinarily powerful magnetic field, cracking under stress, releasing energy in patterns whose statistics happen to resemble some properties of structured communication. That resemblance is itself scientifically interesting. Understanding exactly why a physical process can produce this kind of statistical profile deepens our understanding of both astrophysics and information theory simultaneously. And somewhere out in the roughly 200 billion stars of the Milky Way alone, not to mention the 2 trillion galaxies beyond it, there remains an open question that physics alone cannot answer. Whether any of those stars hosts a civilization that has developed radio technology, and whether any of those civilizations have ever pointed an antenna in a direction that intersects with the expanding sphere of radio waves our own civilization has been sending into space for roughly a century. The mathematics of the search for extraterrestrial intelligence has matured enormously since the early days of simple pulse detection. We now have filters built on information theory, statistical linguistics, evolutionary biology, and artificial intelligence. We have instruments capable of detecting faint signals from across the galaxy. We have computing resources that would have seemed impossible to astronomers of previous generations. What we do not yet have is a confirmed signal that passes every filter. But the tools are getting sharper. The instruments are getting more sensitive. And the question of whether something out there is transmitting, and whether we are capable of recognizing and eventually understanding what it might be saying, remains one of the most important open questions in science. Not because of the drama of first contact, but because the answer changes something fundamental about how we understand our place in the universe. If intelligence arises independently in many places, the laws of physics and chemistry that produced it here apparently tend toward complexity and communication wherever conditions allow. That would be a discovery about the nature of the universe itself, not just about the existence of other beings. The silence so far is data. So is every anomaly we carefully examine and ultimately explain. And the work of building better filters, sharper tests, more sensitive ears pointed at a universe that may or may not be speaking continues. To fully appreciate why the 2017 signal was so striking, it helps to understand just how unusual fast radio bursts are as a class of phenomenon. The first one was discovered entirely by accident in 2007 when astronomer Duncan Lorimer was searching through archived data from the Parkes Radio Telescope in Australia. He was looking for pulsars, the spinning neutron stars that Jocelyn Bell had identified 4 decades earlier. Instead, he found a single burst of radio energy that lasted just a few milliseconds and was far brighter than any known pulsar. It had properties indicating it came from somewhere far beyond our own galaxy, billions of light years away. Lorimer and his colleague Matthew Bales published the discovery and called it a fast radio burst. For years afterward, astronomers were not sure whether these bursts were real astrophysical events or some kind of terrestrial interference. The instruments detected only a handful of candidates, and alternative explanations involving microwave ovens near the telescope or other human-made sources were seriously considered. It took careful work over nearly a decade to establish that fast radio bursts were genuinely coming from deep space. By 2016, the field had confirmed enough examples to be confident they were real. When a fast radio burst arrives at Earth, it has traveled through intergalactic space, which is not truly empty. Space between galaxies contains a thin plasma, a diffuse gas of charged particles. Radio waves of different frequencies travel through this plasma at slightly different speeds. Lower frequency waves are slowed more than higher frequency waves. This means that when a short burst of energy is emitted at a distant source simultaneously across all frequencies, by the time it reaches Earth, the different frequencies arrive spread out in time. Higher frequencies arrive first, lower frequencies arrive later. The amount of this spread, called dispersion, is a measure of how much plasma the signal passed through, which in turn tells astronomers roughly how far away the source is. The dispersion of the 2017 burst was consistent with a source 3 billion light-years distant. The galaxy from which this burst originated is a small, dim, irregular galaxy, far smaller and less structured than the Milky Way. Small, irregular galaxies are known to have high rates of stellar formation and correspondingly high rates of massive star death, which means they produce many neutron stars. This is consistent with the magnetar hypothesis. Young magnetars are thought to be active sources of radio bursts, gradually becoming quieter over thousands of years as their magnetic fields decay. A magnetar's magnetic field is difficult to conceptualize through ordinary comparison. The strongest magnetic field ever created in a laboratory is around 100 Tesla, a unit of magnetic field strength. The Earth's magnetic field at its surface is about 50 millionths of a Tesla. A typical neutron star has a magnetic field of around 100 million Tesla. A magnetar has a field of around 100 billion Tesla, roughly 1 quadrillion times stronger than Earth's field. At these strengths, the magnetic field directly affects the structure of atoms. Electrons, which normally occupy a roughly spherical probability cloud around an atomic nucleus, are forced into thin cylinders aligned along the field lines. Matter itself behaves differently under these conditions. This extreme field creates forces on the magnetar's crust that dwarf anything we can reproduce or fully model. The crust of a neutron star is composed of nuclei packed so densely that they form a crystalline lattice, a rigid structure held in place partly by the enormous gravitational pressure of the star's mass. As the magnetic field slowly shifts and restructures over time, it drags at this crust, building up stress the same way tectonic plates build stress on Earth. When the stress exceeds the crust's strength, it fractures. A starquake occurs. The energy released in a magnetar starquake is staggering. The largest magnetar flare ever detected, from a source in our own galaxy in 2004, released more energy in 0.2 of a second than the Sun emits in 250,000 years. That flare was close enough by galactic standards that it measurably ionized the upper atmosphere of Earth from 50,000 light-years away. A comparable event from a more distant galaxy would produce exactly the kind of intense, brief radio burst we observe as a fast radio burst. The repeating nature of the 2017 source is one of its most scientifically important features, because it allows different types of analysis impossible with a single burst. A one-time event gives you a single fingerprint. A repeating source gives you a library. And the library showed that the bursts were not all the same. They varied in duration, intensity, internal structure, and the spacing between them. This variability itself carries information about the source. The statistical analysis that drew comparisons to language was not measuring whether the signal was trying to communicate. It was measuring whether the distribution of burst properties, their sizes and spacings, followed the same mathematical patterns found in language. And the finding was that it resembled language more closely than it resembled pure random noise. But the researchers who performed this analysis were very careful to note that this is a necessary condition for intelligence, not a sufficient one. Many physical processes, as the earthquake and avalanche examples showed, can satisfy the same necessary condition. Passing the first test is not enough. You have to pass all of them. This is worth dwelling on, because the history of the search for extraterrestrial intelligence has been marked by premature excitement, followed by disappointment. The WOW signal was one example. Another was a signal detected in 2015 by a radio telescope in Russia, which briefly caused excitement before being traced to interference from a military satellite. A series of narrowband signals reported from the direction of the nearby star, HD 178428 in 2020, briefly circulated in the press as a potential alien transmission before follow-up analysis showed they were consistent with interference from human technology. Each of these false alarms has not discouraged the scientific community so much as it has driven the development of better protocols. The SETI Institute and other organizations involved in the search for extraterrestrial intelligence have developed a multi-step verification process for any candidate signal. First, the signal must be confirmed by an independent observatory, ruling out local interference. Second, it must show characteristics consistent with an extraterrestrial origin, such as the appropriate dispersion for a distant source. Third, it must be examined for terrestrial explanations, including satellites, aircraft, and ground-based transmitters. Only after passing all of these tests would a signal be considered for announcement as a genuine candidate of interest. The broader scientific community has sometimes been ambivalent about the search for extraterrestrial intelligence as a research program. For decades, it struggled to obtain mainstream funding, partly because it sits in an unusual position between established disciplines, drawing from radio astronomy, information theory, astrobiology, and linguistics, without fully belonging to any of them. The field received a significant boost in 2015 when the Breakthrough Listen initiative, funded privately, it committed $100 million over 10 years to the most comprehensive search for extraterrestrial signals in history. This allowed researchers to purchase significant time on major radio telescopes worldwide and to conduct systematic surveys rather than relying on opportunistic observations. Breakthrough Listen uses the Green Bank Telescope in West Virginia and the Parkes Telescope in Australia as primary instruments, supplemented by optical telescopes searching for laser signals. It has scanned more than 1 million stars in its first years of operation and accumulated enormous archives of data. Much of the ongoing work is now in the analysis of that data, using machine learning algorithms trained to identify unusual features that human reviewers might miss. The application of machine learning to signal analysis is itself one of the more interesting intellectual developments in this field. The challenge with searching for extraterrestrial signals is that we do not know exactly what we are looking for. Traditional searches have focused on specific signatures, narrowband emissions near the hydrogen frequency, repeating patterns with anomalous regularity, signals that seem to track specific stars rather than drifting with Earth's rotation. But these are all defined by our assumptions about how an intelligent civilization might choose to transmit. Machine learning systems, particularly anomaly detection algorithms, trained on large datasets of known natural signals, can potentially identify features that are simply unusual in ways that human analysts had not thought to specify in advance. This is analogous to how the entropy-based intelligence filter was developed. Instead of specifying in advance what an intelligent signal should look like, the approach defines what natural signals look like and asks whether anything statistically exceptional is present. The training of these systems requires careful curation. If you train an anomaly detector on all available radio astronomy data, you will find anomalies, but many of them will be from terrestrial sources, instrument artifacts, or unusual but entirely natural astrophysical events. The challenge is training the system to distinguish between the kinds of anomalies that are merely unexpected but physically explicable and the kinds that would require a genuinely new explanation. This is an active research problem. One approach that has shown promise is the use of generative models. A generative model is trained to produce realistic samples of natural signals. Once trained, you can measure how surprised the model is by any given input, which provides a mathematically principled measure of how unusual a signal is relative to the distribution of known natural signals. Signals that surprise the model strongly are flagged for detailed analysis. This provides a more nuanced notion of anomaly than simple threshold-based detection. The connection between the tools being developed for extraterrestrial signal analysis and the tools being developed for general artificial intelligence research is one of the more interesting features of the current moment in this field. The large language models that now demonstrate remarkable linguistic capabilities are essentially highly sophisticated versions of the sequential prediction machines that Shannon described in the 1940s. The techniques used to extract structure from whale communication are the same techniques being adapted for potential alien signals. The anomaly detection methods used in signal analysis draw from the same mathematical foundations as the pattern recognition systems used in computer vision and natural language processing. This convergence is not coincidental. All of these problems share a common mathematical structure. There is a source generating sequences of symbols. There is a receiver trying to extract structure from those sequences without full prior knowledge of the source. And there is a fundamental question of how to distinguish structure from noise when the boundaries between them are not sharp. Whether the source is a human writing a book, a whale clicking in the Pacific, a magnetar cracking in a distant galaxy, or a hypothetical civilization encoding a message for whoever might be listening, the mathematical challenge of distinguishing meaningful pattern from meaningless variation is the same. The philosopher's version of this problem is even more fundamental. What does it mean for a pattern to have meaning? Information theory gives us precise tools for measuring how much structure a sequence contains, but it does not tell us what that structure refers to. A perfectly structured, but completely encrypted signal would look identical to an intelligent message from the outside. A message in a genuinely unknown language has all the statistical properties of intelligence, but cannot be understood by a receiver who has no way to learn the code. Shannon's mathematics quantify the form of a message, but not its content. This distinction becomes philosophically important when thinking about contact with genuinely alien intelligence. Even if we successfully detected and verified a signal that passed every statistical filter, establishing that it was produced by a structured, intelligent process, the problem of interpretation would remain entirely open. The interpretation problem is not just about decoding symbols. It is about reconstructing the conceptual framework from which those symbols emerged. A civilization that evolved differently, perceives different sensory modalities, exists under different physical conditions, might organize concepts in ways that do not map onto any human cognitive structure. Their language might encode distinctions that humans cannot perceive, and might lack distinctions that humans consider fundamental. This is not purely hypothetical. We encounter smaller versions of this problem with other species on Earth. Octopuses appear to process color information through their skin despite being colorblind in their eyes, using photoreceptors distributed across their entire body surface. Their experience of color, if they have experience in any philosophically meaningful sense, would be organized around principles completely different from how humans experience color. Bats navigate through a rich landscape of acoustic echoes that humans cannot perceive at all. Dogs track chemical gradients through environments that are essentially invisible to us. The perceptual worlds of other animals on Earth are different enough from human perception that genuine interspecies understanding remains extremely limited despite millions of years of evolutionary coexistence. A civilization from another star system would not share even that limited evolutionary heritage. The starting point for understanding would be whatever is universal in the physics and mathematics that any radio-capable civilization must have discovered. The prime numbers are the same everywhere. The speed of light is the same everywhere. The mathematical structure of quantum mechanics describes the same underlying reality everywhere. Any civilization sophisticated enough to build a radio transmitter must have mathematical knowledge equivalent to what humans have developed, even if they organize it differently. A message built entirely from mathematical relationships would at least have some hope of being recognized and eventually decoded. This is why the most commonly proposed design for a deliberate interstellar message starts with mathematical structure. The Arecibo message, transmitted in 1974 as a demonstration of humanity's radio technology, encoded information about the chemical elements involved in Earth life, the structure of DNA, the physical form of a human, and the solar system, all expressed in binary arithmetic that could be reconstructed from the signal's properties. It was designed to be interpretable by any receiver capable of detecting it, regardless of their biology or cultural background. The response to such messages, if any civilization detected them, would presumably come decades or centuries later, given the speed of light and the distances involved. A signal transmitted toward the nearest star system, Alpha Centauri, would take 4 years to arrive. A response, traveling at the speed of light in the other direction, would take another 4 years. An exchange of messages with a civilization 1,000 light years away would take a minimum of 2,000 years per round trip. These timescales dwarf human civilization. They are measured in geological time. This is one reason why some scientists argue that the search for extraterrestrial intelligence should focus not just on radio signals, but on physical evidence. Technosignatures, which are modifications of the physical environment by technological activity, might be detectable without requiring real-time transmission. Unusual atmospheric chemistry on an exoplanet, artificial light at specific wavelengths on the dark side of a planet, anomalous heat signatures from megastructures in space, all of these might persist for millions of years. A civilization that existed 1 billion years ago would have left radio silence long ago, but might have left physical traces that persist. The most dramatic version of this idea is the Dyson sphere, proposed by physicist Freeman Dyson in 1960, which is a shell or swarm of structures built by a civilization around its star to capture the maximum possible amount of its energy output. A star surrounded by such a structure would be dimmer than expected at visible wavelengths, but would radiate enormous amounts of infrared energy, the waste heat from all that captured power. Several candidate stars have been identified over the years as showing unexpected dimming patterns that prompted speculation about megastructures. Most famously, the star KIC 8462852, nicknamed Tabby's star, which showed irregular, asymmetric dimming that no known natural cause could fully explain for several years. Eventually, a detailed study concluded that dust was the most likely cause. But the episode illustrated how the search for technosignatures can be conducted using existing astronomical data and how natural phenomena can initially appear mysterious before a better explanation is found. The rate at which astronomers are discovering planets around other stars has transformed the statistical framing of the search for extraterrestrial intelligence. When the first confirmed exoplanets were discovered in the 1990s, there was genuine uncertainty about how common planetary systems were. We knew our solar system existed, but whether it was typical or exceptional was unknown. Today, after more than 30 years of observations and multiple dedicated space missions, the data show that planets are extremely common. The Kepler Space Telescope, which monitored roughly 150,000 stars for planetary transits, found that nearly every star in the galaxy has at least one planet. Roughly 1 in 5 Sun-like stars appears to have at least one planet in the habitable zone, the range of orbital distances where liquid water could exist on the surface. Extrapolating these numbers across the 200 billion stars of the Milky Way gives roughly 40 billion potentially habitable planets in our galaxy alone. The numbers are not the difficult part of the calculation. What remains deeply uncertain is how often life arises on habitable planets, how often life that arises eventually develops intelligence, and how often intelligent life develops radio technology. These three transition probabilities are essentially unknown. Life on Earth arose relatively quickly after the planet cooled, suggesting the origin of life may not be rare. But complex multicellular life took nearly 4 billion years to emerge, and technological civilization has existed for only a tiny fraction of Earth's history. The probability of each step may be dramatically different from the others. The Drake equation, formulated by astronomer Frank Drake in 1961 to frame this calculation, combines all of these probabilities into an estimate of how many civilizations in the galaxy might be transmitting radio signals right now. The equation is not meant to produce a precise number. Its purpose is to organize the factors that contribute to the answer and identify which ones we know and which ones we do not. In the 60 years since Drake wrote it, the first factor, the rate at which sun-like stars form in the galaxy, has become well constrained by observation. The fraction of stars with planets and the fraction of those planets in the habitable zone have likewise become well measured. But the probabilities of life arising, of life developing intelligence, and of intelligence developing technology remain almost completely unconstrained by direct evidence. The only data point we have is Earth, and a sample size of 1 is not sufficient to estimate a probability with any confidence. If you know that something happened once, you cannot determine whether it happens rarely, commonly, or inevitably. This is the fundamental epistemological problem at the heart of astrobiology. And it is why the discovery of even the simplest life on another world, a bacterium in the Martian subsurface, or a microorganism in the clouds of Venus, would be scientifically transformative. It would establish that the origin of life is not a singular cosmic accident unique to Earth. Upcoming missions to Mars, Europa, Enceladus, and other bodies in the solar system are designed in part with this question in mind. The detection of biosignatures, chemical or physical evidence of biological processes, is one of the primary scientific goals of solar system exploration in the coming decades. These searches are connected to the search for extraterrestrial intelligence not because microbes are building radio transmitters, but because the probability of intelligence depends entirely on the probability of life, and that is a number we urgently need to measure. The mathematical tools developed for analyzing anomalous radio signals, the entropy filters, the statistical fingerprints, the machine learning anomaly detectors, are being applied in parallel to other domains of astrobiology. Spectroscopic analysis of exoplanet atmospheres is one area where pattern recognition will be essential. When a planet passes in front of its star, starlight filters through the planet's atmosphere, and each molecular species in the atmosphere leaves a specific spectral fingerprint. Detecting oxygen, methane, or other gases that biology produces and maintains out of chemical equilibrium would be powerful evidence of life. Distinguishing these biological signals from abiotic chemistry requires exactly the same kind of careful statistical analysis that signal researchers have been developing. The next generation of space telescopes, including the Nancy Grace Roman Space Telescope and proposed future missions, will have the capability to measure exoplanet atmospheric spectra in detail. The James Webb Space Telescope, launched in 2021, has already provided initial atmospheric measurements of several exoplanets, though none yet with convincing evidence of biology. These measurements will improve rapidly over the coming decade. Looking further into the future, proposed space interferometers arrays of telescopes separated by thousands of kilometers flying in coordinated formation could in principle achieve angular resolution sufficient to directly image the surfaces of nearby exoplanets. This is several generations of technology beyond what currently exists, but it illustrates the direction in which the field is moving. The dream of seeing, rather than inferring, the surface of another world that may harbor life is not physically impossible. It requires solving engineering challenges that have no fundamental barrier, only practical difficulty. The 2017 signal remains in the scientific literature as an interesting anomaly, fully explained by magnetar physics, but worth studying further to understand the mechanisms by which strongly magnetized neutron stars produce structured burst sequences. The statistical analysis that showed similarities to language patterns has been refined and extended. The consensus is that natural astrophysical processes can produce signals that pass simplified versions of the intelligence filter, which is itself a scientifically valuable result. It tells researchers that the filter needs to be more rigorous than Zipf's law alone, and pushes the field toward the deeper Shannon entropy analysis as the more reliable discriminant. The next version of the filter is likely to incorporate additional mathematical tools drawn from network theory, dynamical systems theory, and computational linguistics. Any genuine signal from an intelligence would presumably show not just the right frequency distribution and the right entropy profile, but also the right kinds of long-range correlations, the right fractal properties, and the right information content when analyzed at multiple scales simultaneously. Building these tests into an automated analysis pipeline that can run in real time on incoming telescope data is one of the near-term engineering goals of the field. One of the more remarkable aspects of this entire research program is how it has driven genuine scientific progress in areas far removed from the original goal. The mathematical tools developed to look for intelligence in radio signals have been applied to finance, to neuroscience, to the analysis of genetic sequences, and to the study of animal communication. The fundamental question of how to distinguish structured information from noise is important far beyond astronomy. Every field that deals with complex data streams grappling with background noise has something to learn from the methods developed by radio astronomers and information theorists working on this problem. The search for extraterrestrial intelligence has also pushed the development of new computational infrastructure. The distributed computing project, SETI at Home, which ran from 1999 to 2020, enrolled millions of personal computers around the world to analyze radio telescope data, collectively contributing processing power equivalent to a supercomputer. Although the project did not find a confirmed signal, it demonstrated the model of crowdsourced scientific computing and paved the way for similar distributed computing projects in fields from protein folding to climate modeling. Modern signal analysis has moved entirely to cloud computing and purpose-built hardware. But the principle of distributing a scientifically important computational problem across many processors remains central to the field. The volumes of data produced by modern radio telescopes are too large for any single computing system to analyze in real time. The square kilometer array will produce data at rates that exceed the global internet traffic of 2010. Managing, storing, and analyzing these data streams requires infrastructure that does not yet fully exist and will need to be built in parallel with the telescope itself. The timeline for this infrastructure development coincides with a broader transition in how large-scale scientific computation is done. The machine learning revolution of the past decade has produced tools and hardware, particularly graphics processing units adapted for neural network training, that are equally useful for signal processing and anomaly detection in radio astronomy. The same data centers that train large language models can, with appropriate software, analyze radio telescope archives for unusual patterns. This convergence of technology is accelerating the pace at which the search for extraterrestrial intelligence can be conducted. Where previous generations of researchers could scan perhaps a few hundred star systems per year with detailed analysis, modern systems can scan millions. Where previous analysis could look for simple patterns, like narrowband signals at specific frequencies, modern systems can look for subtle statistical regularities across the full complexity of a received signal. The filter has grown from a blunt instrument into something considerably more refined. Whether the universe will eventually provide a signal that passes this refined filter remains completely open. The silence so far, meaning the absence of a confirmed detection after more than 60 years of increasingly sensitive searching, is itself a scientific datum that constrains the distribution of technological civilizations in the galaxy. If technological civilizations were extremely common, and if most of them produced detectable radio emissions for millions of years, we would likely have found something by now. The silence suggests either that such civilizations are rare, or that they do not produce detectable emissions for long, or that they transmit in ways we have not been searching for, or that we have simply not been searching with sufficient sensitivity over sufficient time. This uncertainty is sometimes called the Fermi paradox, after physicist Enrico Fermi, who reportedly asked at lunch in 1950, "Given how many stars and planets exist and how much time has passed, where is everybody?" The answer continues to be unknown. But unlike many questions where uncertainty represents simply a gap in knowledge, this particular uncertainty sits at the intersection of physics, biology, chemistry, information theory, and the deepest questions about what intelligence is and what it tends to do when it arises. Answering it, if we ever do, will not just tell us whether we are alone. It will illuminate the nature of life, the nature of mind, and the nature of a universe that appears to be rich with the raw materials and physical laws necessary for both. Every anomalous signal that gets carefully analyzed and ultimately explained strengthens our understanding of what the universe naturally produces. Every new mathematical tool that gets developed to distinguish intelligence from noise sharpens our ability to recognize either one when we encounter it. And every improvement in telescope sensitivity and computational power extends the reach of what we can listen to. The universe has been generating radio waves for more than 13 billion years. We have been listening for less than 100. The search has barely begun. To understand why the entropy-based filter works as well as it does, it is worth spending more time with what Shannon actually measured and why it captures something deep about the nature of language. Shannon was working in the late 1940s on problems of communication engineering. The practical question was how to transmit messages efficiently and reliably across noisy channels. But his mathematical framework turned out to describe something far more fundamental than telephone lines. Shannon defined entropy in information theory by borrowing the term from thermodynamics, where entropy measures disorder. In thermodynamics, a high entropy state is one where many different arrangements of atoms are equally likely, while a low entropy state is one where very few arrangements are possible. Shannon's insight was that the same mathematical structure describes the surprise or unpredictability of messages. If every symbol in an alphabet is equally likely to appear next, the entropy is maximum. You gain maximum information from each new symbol because nothing was predictable. If certain symbols are overwhelmingly more likely than others, the entropy is lower. You gain less new information from each symbol because the next one was partly predictable in advance. The key extension Shannon made was to sequences. A sequence has higher order entropy properties that single symbols do not. The entropy rate of a sequence is the average amount of new information provided by each additional symbol given all the previous ones. In a language, knowing the previous 10 words tells you much more about the next word than knowing just the previous one word. So the entropy rate drops as you condition on longer histories. In noise, knowing the previous 10 values typically tells you only marginally more than knowing the previous one value, so the entropy rate stays roughly flat. This is what makes the entropy depth curve such a powerful discriminant. It does not just measure how often each symbol appears. It measures how the predictability of the sequence grows as you look further back in history. Language is deeply structured in the sense that distant symbols constrain each other. The word at the end of a sentence is constrained not just by the preceding few words, but by the entire topic and context of the surrounding paragraph. Noise, no matter how complex its local statistics, does not have this property. The distant past in a noise signal is not predictive of the future. The practical measurement of this curve requires choosing what to use as symbols. In an alien radio signal, we do not know in advance what the natural units of the message are. In human language, letters and words are natural units because we know the language. In whale communication, the natural units, which are specific click patterns called codas, had to be identified by researchers through detailed acoustic analysis before the entropy calculation could be applied. In a radio signal from an unknown source, identifying the natural symbolic units is itself a research problem. One approach used in analyzing fast radio bursts is to use the burst events themselves as symbols, characterized by their properties such as duration, peak intensity, and internal structure. Each burst gets categorized into a class based on these properties, and the sequence of classes is then analyzed for entropy properties. This approach assumes that the discrete bursts are the natural symbolic units of whatever process is generating them, which is reasonable if the source is a magnetar, but might not capture the right level of structure if the source were something more complex. A more sophisticated approach, which researchers are currently developing, is to apply the entropy analysis at multiple scales simultaneously. At the finest scale, the analysis looks at the internal structure within each burst. At intermediate scales, it looks at sequences of bursts within a single episode. At the coarsest scale, it looks at the timing and grouping of episodes over long periods. A natural source would be expected to show consistent statistical properties at each scale, determined by the underlying physical process. An intelligent source might show different statistical properties at different scales, reflecting the hierarchical structure of language, where phonemes make up words, words make up sentences, and sentences make up larger discourse structures. This multi-scale approach has a parallel in how linguists analyze human language. Phonology is the study of the smallest sound units. Morphology is the study of how those sounds combine into meaningful word parts. Syntax is the study of how words combine into sentences. Semantics is the study of meaning. Each level has its own statistical properties and its own entropy structure. A complete analysis of an unknown communication system would ideally characterize all of these levels, even without initially knowing how to interpret any of them. The application of this framework to animal communication has been one of the more productive areas of research in recent years. Sperm whales are not the only species whose communication has been analyzed this way. Researchers have applied similar methods to bottlenose dolphin whistles, humpback whale songs, chimpanzee calls, corvid vocalizations, and the songs of various bird species. The results have been illuminating. Some species, notably the great apes and dolphins, show entropy properties broadly consistent with simple symbolic communication. Others, particularly songbirds, show highly structured patterns that are not consistent with the symbolic communication model, but may reflect a different kind of information encoding, perhaps related to individual identity or fitness signaling rather than propositional content. The work on sperm whales has attracted particular attention because their communication system appears to be especially complex. Sperm whales live in tight social groups and produce elaborate click sequences during social interactions. The clicks are organized hierarchically into codas, which combine into exchanges, which in turn make up long-term patterns of interaction between individuals. Preliminary analysis suggests that the statistical structure of sperm whale communication shares some properties with human language that simpler animal communication does not, while differing from human language in other ways that researchers are still trying to characterize. The MIT project that trained a large language model on sperm whale vocalizations achieved something that no previous analysis had managed. It could predict, with meaningful accuracy, what a whale was about to do, based on the preceding sequence of vocalizations. This is a lower bar than translation, but it is an important lower bar. It establishes that the vocalizations carry behavioral information that has detectable structure. Whether that structure encodes propositional content in the way human language does, meaning statements that can be true or false about the state of the world, remains unknown. This research program illustrates a general principle that is increasingly important in the search for extraterrestrial intelligence. We should use Earth life as a testing ground for the tools we plan to use in space. Every species whose communication is analyzed with the entropy filter, and whose results are compared with what we know about their biology and behavior, gives us another calibration point. Every success, where the filter correctly identifies structured communication, and every failure, where the filter misclassifies something, teaches us something about the filter's limitations and how to improve it. The most important calibration, which we still lack, would be a communication system that is clearly not produced by biology, not produced by known physics, and that passes the intelligence filter with high confidence. That would tell us the filter works not just for Earth life, but in a broader context. Without such a calibration, we are applying tools we have validated only in the narrow context of Earth biology to potentially much stranger phenomena. This is a deep problem in the philosophy of science, as applied to the search for extraterrestrial intelligence. We are trying to search for something we have never seen, using methods calibrated entirely on examples from a single planet with a single evolutionary history. The best we can do is to make our methods as theoretically well-grounded as possible, and as transparent as possible about their assumptions, so that when we do apply them to anomalous data, we can be honest about what level of confidence the results warrant. The scientific culture around the search for extraterrestrial intelligence has matured considerably on this point. Early researchers sometimes allowed enthusiasm to outpace caution, and the field suffered reputational damage from premature announcements that were not reproducible. The current standard requires independent verification before any candidate signal is taken seriously. And even then, The bar for claiming intelligent origin is understood to be extraordinarily high. Extraordinary evidence would be required for an extraordinary claim. This caution is appropriate, but it creates a certain tension. The filter we have built is conservative by design. It is designed to avoid false positives, to avoid claiming intelligence when the evidence does not unambiguously support it. But a conservative filter may also generate false negatives, rejecting signals that are actually intelligent because the evidence falls just short of the threshold. If a genuinely intelligent signal were to arrive in a form that did not exactly match our theoretical expectations, our filter might classify it as natural. Managing this trade-off between false positives and false negatives is one of the ongoing methodological challenges of the field. In statistical terms, this is the sensitivity-specificity trade-off, and there is no perfect solution. The goal is to understand the properties of the filter well enough to know, when a result comes in, exactly what level of confidence it warrants. A result that barely passes the threshold should generate much less confidence than a result that passes with overwhelming margin. What would it take for a signal to pass with overwhelming margin? It would need to show entropy properties that are not only different from known natural sources, but that are consistent with the specific mathematical properties we associate with structured symbolic communication. It would need to show these properties across multiple independent analyses at multiple scales. It would need to be reproducible across multiple independent instruments, and it would need to resist every natural explanation that researchers could devise. Even then, the conservative scientific position would be that an extremely unusual natural source cannot be definitively ruled out. The history of astronomy is full of phenomena that initially seemed to require extraordinary explanations and turned out to have elegant, natural ones. But science also recognizes that eventually, if all natural explanations fail and the mathematical properties keep pointing in the same direction, the hypothesis of intelligence becomes the most parsimonious explanation. This is how discovery works in any field. Evidence accumulates. Competing hypotheses are tested and ruled out. At some point, the remaining hypothesis, however surprising, is the one that the evidence best supports. The history of science has repeatedly shown that the universe contains things we did not initially believe possible. Pulsars were initially thought to be too precise to be natural. Black holes were initially considered mathematical curiosities with no physical reality. The cosmic microwave background, the afterglow of the Big Bang, was initially dismissed as equipment noise. Each of these required a recalibration of what physicists considered physically possible. If the universe has arranged for intelligence to arise in other places, discovering that fact would likely require a similar recalibration of our assumptions about what is natural. The mathematical work on signals, information, and intelligence continues to develop in parallel with the technological improvements in telescope sensitivity and computing power. Shannon's entropy framework has been extended into more sophisticated measures of information. Researchers in the field of algorithmic information theory, building on work by Kolmogorov, Chaitin, and others, have developed measures of algorithmic complexity that capture something deeper than statistical entropy. The algorithmic complexity of a string is related to the length of the shortest computer program that could generate it. A truly random string has maximum algorithmic complexity because no program shorter than the string itself can produce it. A highly structured string can be compressed into a short program that generates it. Language falls in between, complex but compressible, reflecting the way it balances novelty and structure. Applying algorithmic complexity measures to radio signals from space is theoretically appealing but computationally very challenging, because computing algorithmic complexity is in general an unsolvable problem in the mathematical sense. You can always find shorter programs than the ones you have already found, but you can never be certain you have found the shortest. Practical approximations exist, based on lossless compression algorithms, but they have known limitations that become significant when applied to genuinely novel data. This is an active area of research that connects the search for extraterrestrial intelligence with the foundations of theoretical computer science. The physical picture of what we might be looking for has also expanded beyond radio waves. When Morrison and Cocconi wrote their 1959 paper, radio was the obvious choice because it was the communication technology that humans had most recently mastered, and because it propagates well through interstellar space. But in the decades since, laser technology has advanced to the point where optical and near-infrared laser pulses can in principle outperform radio for interstellar communication over short distances, particularly if the sender wants to transmit enormous amounts of information quickly. A laser pulse lasting a nanosecond can carry significant information and would be extraordinarily bright for that instant, potentially detectable across tens of light years. Searches for optical technosignatures? Bright flashes in the optical or near-infrared that do not match any known stellar source are now conducted alongside radio searches. Several dedicated optical SETI telescopes have been built, including instruments at the Harvard-Smithsonian Center for Astrophysics. These instruments monitor millions of stars for brief, anomalous optical flashes. No convincing candidate has been found, but the searches have only recently achieved the sensitivity needed to detect realistic signals. Beyond radio and laser, theorists have proposed other possible communication channels. Neutrinos are particles that pass through matter almost without interaction, making them capable of carrying signals through the bulk of a planet without being absorbed. A sufficiently advanced civilization might use neutrino beams for communication. Detecting them requires enormous underground detectors, and searches for structured neutrino signals are in their infancy. Gravitational waves, ripples in space-time produced by accelerating masses, were detected for the first time in 2015 and open another possible channel that no civilization dependent on electromagnetic radiation would naturally think of. The physics of generating gravitational waves strong enough to transmit information across interstellar distances is far beyond anything humans can currently do, but a civilization millions of years more technologically advanced might have mastered it. These speculative channels illustrate a general point. The space of possible communication modalities is large, and we have searched only a small part of it. Our searches have been concentrated in the part most accessible to our technology, which may or may not overlap with the part that other civilizations use. This is one of the reasons why a negative result, after decades of searching, is difficult to interpret. It might mean intelligent transmitters are rare, or it might mean they use modalities we have not searched, or transmit in directions we have not monitored, or broadcast at power levels below our current sensitivity. The concept of a galactic radio dial is useful here. Different frequencies of electromagnetic radiation travel through the interstellar medium with different degrees of interference and absorption. The region between roughly 1,000 MHz and 10,000 MHz, which includes the hydrogen frequency and the hydroxyl frequency just above it, is sometimes called the cosmic water hole. Because water is composed of hydrogen and hydroxyl, and because this part of the spectrum is relatively clear of astrophysical noise, Morrison and Cocconi's original argument for the hydrogen frequency and subsequent arguments for the wider waterhole region assume that a communicating civilization would choose frequencies that minimize interference and maximize the chance of detection. This is a reasonable argument, but it is an assumption. A civilization whose evolution led them to think about communication differently might choose other frequencies. Broadening the search to cover more of the radio spectrum is one of the directions in which current technology is moving. The square kilometer array will be capable of monitoring a very large fraction of the radio spectrum simultaneously, which removes the need to make assumptions about exactly which frequency a transmitter might use. Similarly, the combination of optical and radio searches removes the assumption about which part of the electromagnetic spectrum is being used. The temporal aspect of the search is equally important. Radio surveys typically observe each patch of sky for a limited time before moving on. A transmitter that broadcasts only briefly, or that transmits in a pattern that happens to be aimed at Earth only occasionally, might be missed. Surveys that return to the same targets repeatedly over years and decades, building up long baselines of observation, are better positioned to detect intermittent sources. The repeating fast radio burst from 2017 was first detected in a single observation, but its significance became clear only through subsequent monitoring over months and years. Building up long baselines of observation for thousands of stars simultaneously is exactly what survey telescopes, like the Square Kilometer Array, are designed to do. The combination of high sensitivity, broad frequency coverage, large sky coverage, and long temporal baselines represents a qualitative improvement over everything that has come before. If technological civilizations are present in our galactic neighborhood and are transmitting in any form we can detect, the next generation of instruments gives us a better chance of finding that signal than all previous efforts combined. The emotional and philosophical weight of this search is not something that science alone can fully express. The possibility that the universe contains other minds, other ways of organizing experience and knowledge, other histories of discovery and creation, touches something deep in the human understanding of our own significance. We are the only species we know of that looks at the stars and wonders whether anyone is looking back. Whether or not that wondering is ultimately answered with a detection, the act of asking the question rigorously and building tools precise enough to have a real chance of finding an answer is itself a remarkable expression of what intelligence does when it reaches sufficient complexity. It turns outward. It asks, what else is there? And it builds the instruments needed to listen. There is one more thread worth following: the way this search has quietly changed how scientists think about intelligence itself. Before we had tools to measure the mathematical structure of communication, intelligence was discussed mostly in qualitative terms. We knew it when we saw it, or thought we did. The development of Shannon entropy, Zipf analysis, and their extensions gave researchers something precise to point at. Intelligence is not just complexity. It is structured complexity with specific mathematical properties. It is complexity that grows more predictable at deeper scales, rather than staying uniformly unpredictable like noise. It is complexity organized around symbols that recur in patterns constrained by context. This precise definition has consequences beyond the search for extraterrestrial signals. It has informed debates in cognitive science about what kinds of processes count as intelligent. It has been used to analyze the outputs of machine learning systems, to ask whether they are genuinely producing structured language or sophisticated noise. It has been applied to the fossil record to look for evidence of behavioral complexity in extinct species. The tools built to search for alien minds have found application in understanding the minds that already exist on Earth. The large language models that researchers are now proposing to use in the interpretation of anomalous signals are themselves the most striking example of this circular enrichment. Shannon described the mathematics of a machine that would capture the deep structure of language. Researchers, trying to understand language, developed those machines. The machines turned out to capture something about the geometric structure of meaning that no one had fully anticipated. And now those machines are being pointed outward, towards signals from across the universe, to see whether the geometric structure of meaning might be present in forms no human has yet encountered. This is what the scientific enterprise looks like when it is working well. A question that seems impossibly large, are we alone in the universe, generates precise tools for measuring specific properties of specific signals. Those tools turn out to illuminate something fundamental about the nature of the thing being searched for. And the search itself expands the boundaries of what we understand, regardless of whether the target is eventually found. The universe has had 13.8 billion years to arrange matter and energy into complex structures. Life on Earth took about 4 billion years to produce technology. Those numbers leave an enormous amount of time for other arrangements to have occurred in other places. Whether any of those arrangements produce something capable of sending a message that another civilization might someday receive and recognize is a question that physics permits but does not require. It is a question that only observation can settle. The tools are sharper now than they have ever been. The instruments are larger, the computers are faster, the mathematical filters are more refined. And somewhere in the data streams flowing continuously from radio telescopes pointed at the sky, in archives accumulated over decades, and in observations being made right now, there may or may not be a pattern that passes every filter, a signal that no natural process we know of could produce, a mark left by another mind. Finding it, if it is there, will require everything that science has built in a century of careful listening. Not finding it will tell us something important too, about the rarity of what we are, or about the limits of how far our listening has reached. Either way, the search continues, and that is exactly what it should do.